This lab by motion of falling objects. The observation are two objects in free fall and the rate at which their velocities are changing. Object number 1 is a ball, which is a rapidly falling object. Object number 2 is a piece of paper, which is a slow falling object. Both objects are initially at rest and are held above the ground at some height. The result is that the slow falling object has reached some constant velocity, while the rapidly falling object did not. This is because the slow falling object has achieved or has been facing some counterbalancing force, which is going upward to counterbalance that force due to gravity. That constant proportion is much greater, probably due to surface area for that slow or for the slow moving object. If you look at the fast moving object here, you can see that the origin is chosen to be the center of the ball, and the calibration stick is 0.07 meters, and the negative y-axis is going downward. And then you can see that within each frame is a 0.05 seconds difference. So the time step is 0.05 seconds going downward on the negative y-axis. If you look at the quick slow-moving object, you can see that calibration stick is 0.2794 meters. The negative y-axis is going down once more, and the origin is chosen to be the center of that piece of paper. The time step is exactly the same. So you can see it going down like that with the same time frame. Now, to code this, I simply took the forces, which is the force due to gravity, and the force drag, which is just some v constant times the speed, and negative mg is the force, and then due to gravity, and then the net force is the sum of those two. Then I modified Newton's second law to find to update the velocity and to update the position. So I start with F net equals ma, multiplied both sides by delta t, then divided both sides by the mass and added velocity to yield that final velocity equal to initial velocity plus F net delta t over m. And then to find the positions, I multiplied by delta t once more and yielded this equation. And then I assume that v average is equal to v final and v initial because delta t is so small. And then I repeat this until t is achieved. So you can see that for the ball with no gravity, for the ball and paper, the initial position is here. Ball's mass is given in kilograms, 0.318. As stated, here's the velocity and position. And the force due to gravity is equal to the force net in this first example. So you can see that the curve is very parabolic in this sense, and this will occur also most likely for the paper due to gravity. Here is the delta t once more. The position is at 0, and the mass is 0.0048 kilograms. So that's very parabolic as well. Now, if you look at the code when you include drag, it's just a constant is shown to be 0.0099. Drag is b times the magnitude of the velocity. F net equals drag plus gravity, as I stated before. It's still actually very parabolic. That is because the drag force is very small for this time. And then for this one, I included the drag force, which counteracts very quickly to reach that terminal velocity, which is consistent with that model, with the video or observation shown. And if you look at the data, you can see that the ball with no drag compared to the ball with drag is roughly the same because the drag was so small for that time. Now, the paper with no drag is a terrible fit because the drag is what yielded that constant velocity, because once I added drag, you can see that there is no more acceleration because it has reached terminal velocity. Now, to answer the what if question, I created a code that looked at it with gravity and without gravity. So if I threw it, that object with a, so I gave it a velocity. So I gave it a velocity of -4 starting because I threw it down, initial velocity -4. You can see that it, it definitely accelerates, and it goes down a little more because of that acceleration, and it continues to accelerate, or it continues to increase its velocity. Now, once I actually add that drag force with throwing at that same initial velocity, you can see that yes, it is thrown at first, but then it reaches that velocity, terminal velocity again. And if you look at the graph and compare the data, you can see that it does indeed yield a difference. Here is it without the terminal velocity, or without the drag, and here is it with the drag. So to answer what that means, you can see that for the slowly falling object, the velocity becomes constant. This is because the magnitude of the force due to gravity and drag eventually become equal for the slowly falling object. The force of drag is applied upward, whereas the force of gravity is applied downward, thus F net equals 0. That is the meaning of terminal velocity. The object can no longer accelerate. Hence, the constant velocity, thus constant slope, is given by the plots. The momentum will thus be constant as well, and the plots, along with the observation, is consistent with these findings.